Hello, everybody. This is Miss Peachy from your WCA physics class. So I thought I would bring you this next video in our little video tutorial series, just kind of using a pretty old school method of recording my notebook because, I don't know, the last one I gave you was having some technical issues. So I don't usually have lots of technical issues with my notebook. So just go ahead and do it this way for now. So today the topic we're talking about is acceleration. Okay, and acceleration is a change in velocity. What acceleration isn't always, however, is speeding up and slowing down. Okay, so keeping in mind that when you have something that's changing its velocity, velocity is a vector. So it's a measurement of both the change in position over change in time, and it's a measure of the direction that that object's moving. So if an object changes direction, we say it's accelerating even if its velocity remains constant. The old kind of example here, right, is if I have a racetrack and I have a car that's like driving around the racetrack and it's maintaining a constant speed. It's a really slow race car, but it's maintaining a constant speed of, say, 50 miles per hour. It's just kind of, it's like the pace car almost. It doesn't change its speed. However, it is accelerating because it's changing its direction. Because remember, acceleration, like velocity, is a vector. So it accounts for changes in speed, but also in the direction. So how do we write the equation for average acceleration? Very much like we did the equation for average velocity. Average acceleration, A with subscript AVG, that tells us its average, remember that denotes something specific, is equal to delta V over delta T. So in this case, it's showing us its change in velocity over change in time. Change in velocity over change in time. We can write that a little bit more, kind of write it out with more detail by writing V sub F, final velocity, minus V sub I, initial velocity, over T sub F minus T sub I. Okay, because remember those subscripts tell us when we're taking those measurements. We're taking them at the final point in that particular journey, and we're taking it right at the beginning of the journey, and so on and so forth. Now, the units here for acceleration differ slightly from those of velocity. The unit for velocity is meters per second. The unit for time is seconds. So the units for acceleration are meters per second per second. Now, I absolutely adore this way of noting acceleration, or the units for acceleration. I love this because it's very literal. Because by looking at the units here, you can easily see the formula of delta V over delta T. However, for mathematical reasons, sometimes it's easier to change kind of how this looks. So I'll write it like this, meters per second. And remember that if I have seconds in the denominator, it's like multiplying by 1 over seconds. And when you do that, you end up with meters per second squared. So you'll more likely and more often see them, the units for acceleration, written like that, meters per second squared. All right, so let's look at a little problem here, a little example problem. Okay. A shuttle bus slows down with an average acceleration of negative 1.8 meters per second squared. How long does it take the bus to slow from 9 meters per second to a complete stop? Okay, so a shuttle bus slows down with an average acceleration of negative 1.8 meters per second squared. How long does it take the bus to slow from 9 meters per second to a complete stop? So let's start by looking at our givens here. Okay, what are we given? What information? We know that the initial velocity, v sub I, is 9 meters per second, 9.0 meters per second, because that's what it's going to start out at, and it wants to stop. We know that the final velocity, because we want it to stop, will be 0 meters per second. And we know that its average acceleration is given as negative 1.8 meters per second squared. Okay, so let's look at this. Remember, the equation for average acceleration is delta V over delta T. Final velocity minus initial velocity, right? So our final velocity, 0 meters per second. Our initial velocity, 9 meters per second. And we don't know time. Don't know delta T. But we do know that this is equal to negative 1.8 meters per second squared. So to solve for delta T, we really need to multiply the left side of this by delta T. We're essentially cross-multiplying here. The right side by delta T, right? And then divide both sides by negative 1.8. Okay, when we do that, we end up with delta T equals negative 9 meters per second divided by negative 1.8 meters per second squared. Where's my calculator? It's hiding here. That gives us 5.0. In this case, I'm sorry, meters per second squared. Meters per second divided by meters per second is the same as multiplying by the reciprocal, remember? So these cancel, this cancels, and it just gives us seconds as our final unit of measure. So it takes 5 seconds to slow down. It's a stopping point. That gives you a good example of average acceleration. So you might wonder, how do we know if acceleration is positive or negative? In what what circumstances can we figure that part out? Like, how do we know? So a good example of this is remembering that positive acceleration doesn't always mean speeding up, and negative acceleration doesn't always mean slowing down, right? Positive doesn't always mean speeding up, and negative doesn't always mean slowing down. So we're going to look at this. We're going to look at, first of all, thinking about this as motion along a single dimension. So just like walking along a number line. So in the middle at 0, if I go to the left, that's the negative displacement. If I go to the right, it's positive displacement, right? So I'm going to have a column in my table for displacement. I'm going to have a column in my table for speed. And I'm going to have a column in my table for acceleration. Actually, I should probably call this. Yeah, I think that's a good one, because those kind of go together. So if I'm moving towards the positive end, if my displacement is positive, and I'm speeding up. So speeding up with positive gives us a positive acceleration. Okay. If I'm going in the opposite direction, towards the negative, so I'm going a negative displacement, and I'm speeding up, so actually I'm increasing my speed. Actually, take that back for a second. Hang on. Okay, sorry, I kind of tripped myself up a little bit there. But if I'm going in the opposite direction, if I'm moving in the opposite direction, that means my velocity is essentially negative and I'm slowing down. So this, we'll just call this speed up or slow down, right? So that's what I mean by positive and negative speed, either speeding up or slowing down, if that makes sense. But if I'm doing that, if I'm moving in this direction, meaning that I would have a negative velocity, right? But I'm also slowing down, then actually I have a positive acceleration, believe it or not. So they kind of cancel each other out. So I'm slowing down. So I'm going to put speed up / slow down, because I feel like even though I'm saying negative, I just want you to have a really good idea of what I mean by that. So whenever the signs are the same, right, displacement really refers to kind of your velocity here. Because remember, direction, how much the direction you're moving is very important with velocity too. So it's, if you are moving in this direction, you have a negative velocity. If you're moving in this direction, you have a positive velocity, right? So that's what we're talking about there. All right, so if I'm moving in this direction, positive velocity, but I'm speeding up, I have positive acceleration. If I'm moving in this direction, negative velocity, and I'm also slowing down, I have a positive acceleration, because the two signs kind of cancel each other out. In the other two situations, you'll have a negative. So if you're going in this direction, but you're slowing down, you have negative acceleration. If you're moving in the negative direction, but you're speeding up, you have negative acceleration. So wherever the two signs are alike, positive. Wherever the two signs are opposite, negative. So if you're trying to figure out whether or not your acceleration is positive or negative, just ask yourself, well, is my velocity positive or negative? And am I speeding up or slowing down? So hopefully that makes some sense, okay? It's also kind of counterintuitive in lots of ways, because sometimes you're incorrectly taught in the past that speeding up means positive and slowing down means negative, but it really doesn't. It's more of a frame of reference than anything else. But that's kind of a good rule of thumb. All right, so we're going to continue the next video talking a little bit about displacement with constant acceleration. We're going to be looking at and getting into what are known as the kinematic equations. So we have two more short videos here. The first one's just talking about displacement with constant acceleration, and then we get into some free fall problems kind of towards the end. So I hope that all made some sense to you and it's been helpful. Let me know if it is. I like the feedback. You can send me a webmail to let me know if this was helpful. And I hope you have a great day.